This video is about deriving what I like to call power tools, or some fancy equations to put on your toolbox, your equation card. Why am I showing you the derivation today? Well, the equations themselves are going to be really helpful to you in the end. And through the derivation, I want you to see that the equations, I'm not just pulling them out of a book, they actually come from someplace. And they come from the definition of the concepts we've been working with: average velocity, acceleration, and the like. And also it gets us to practice some algebra. First, since we're just dealing with introductory physics in these videos, we're only talking about acceleration that's uniform. That is a smooth, constant acceleration. When you accelerate in your car by pressing on the gas pedal, when your car shifts gears, that acceleration, you have this little jerk and the acceleration changes a bit. But for us in introductory physics, we're only going to be working with things that smoothly accelerate. So the acceleration itself is constant. The velocity might be changing, but the acceleration is constant. And under that system, this equation down here is true. And it's basically another way of calculating average velocity. It just says the average velocity is the original plus the final divided by 2, which is how you would take an average, say, of 2 test grades. You would add the first test, the second test, and you divide by 2. And so this equation is true as long as acceleration is constant. And I have an example here. So if the velocity is 4 meters per second and 8 meters per second is the final, then we add 4 and 8, which is 12 divided by 2, and we get the average velocity of 6 meters per second. So that's just a simple additional equation that we have to work with, to work from, to calculate average velocity. Recall the equations that we had before, our 3 basic tools. So we defined average velocity as displacement divided by time. I'm going to call that equation 1. So make sure that when you write that down, you number it, because I'm going to be referring to these throughout the video. The second equation, another equation for average velocity, is for original plus final velocity divided by 2. And then our definition for acceleration, which is the change in velocity, that is the final velocity minus the original velocity, divided by the time it takes to make that change. We're going to be using these 3 equations to derive or put them together to make more advanced equations that we'll use in the course. Just as a side note, you'll notice that when I write T for time, to abbreviate time, I always put the little curl on the bottom, and I would encourage you to do that as well. I really think that's a good idea, because sometimes it's confusing when other students or I'm looking at your work. And if you write a T like this, if you make it identical to a plus sign, then I'm not going to be able to tell if that's a plus sign or a T. And sometimes students make mistakes because they do that too. So I highly encourage you to put that little curl on the end of a T there to indicate that's time and not a plus sign or an addition sign. Well, I think it might be better just to drop it today. All right. Here's our motivation for this power tool, for the first one. Imagine that we have a car, and it starts from rest, no velocity, and it accelerates at 10 meters per second squared, 10 meters per second every second, for a displacement of 5 meters. So it goes 5 meters as it's accelerating. How fast is it going now? How fast is it now going? Well, if we apply the guess method, which is what I encourage you to do, we would list our givens and our unknowns. And so the original velocity is 0 because it says it starts from rest. The final velocity is what we're looking for. That's our unknown. The acceleration we're told is positive 10 meters per second squared, and the displacement is positive 5 meters. The next step would be to find an equation. And ideally, we would want an equation that would have VO, VF, A, and delta X in it. And if you remember from your 3 equations, we don't have an equation like that. We don't have an equation with those 4 things in it, but we can derive one. So that's what I want us to do on this next board. And it looks a little complicated, but I want to encourage you to pause the video if you need to, and make sure that you're following the steps as I go along. So we're going to put those 3 simple equations together to make a power tool, or a more advanced equation. And so I'm going to start with equations 1 and 2. They're both average velocity equations. And so I can write the equality. It makes sense, doesn't it, to say average velocity is average velocity. That's a true statement. And so equation 1, though, average velocity is delta x over t, and in equation 2, average velocity is VO plus VF over 2. And so if I take this equation here, where I've just put these two together, and I cross multiply, I'm assuming you remember how to cross multiply. So that's 2 delta x on the left side, and then t times this quantity on the right side. Okay, so that's combining 1 and 2 into an equation. But what about the third equation? What about the acceleration equation? So that's over here. If we rearrange that acceleration equation, a equals vf minus vo over t, we multiply both sides by t, cancel it on the right. Then we divide both sides by a, cancel on the left. We get this equation for time. This t equals vf minus vo over a. So that's just taking equation 3, rearranging the pieces, and turning it into an equation for time. Time equals that. I'm then going to make a substitution. I'm going to take this t here, this vf minus vo over a, and I'm going to substitute it back into the other equation where we put equations 1 and 2 together. So I'm going to get rid of this t and replace it with what's in purple over here. I do that right there. So this is the same equation. I just replace the t with vf minus vo over a. And then I do some algebra. So the first thing I did is I multiplied both sides by a, which canceled a on the right side and give me an a on the left side. And then the next thing I did is that I multiplied these out. What do you call that? FOIL method or something? First outside, inside last. And so I multiplied those out. I canceled some things that canceled. And what I got was vf squared minus vo squared. Now if you're unsure about this step, you can either ask me in class or you can take a few moments, pause the video, see that you can get this answer from that. And in the end, we rearrange things to typically write it this way. This is the standard way to write it. So final velocity squared is original velocity squared plus twice the acceleration times the displacement. This is boxed. You should put it on your equation card, on your toolbox. We got done with that one. How's that going to help us? Well, remember, we started going after this because of this question from the previous slide. So the equation we can now use is the new one that we derived. Vf squared equals Vo squared plus 2a delta x. And then we can substitute our values. So Vf squared is what we're looking for. Vf. Vo is 0 squared plus twice the acceleration times the displacement. Now when we solve, all we have to do, since we put in all our values, is we have Vf squared equals 0 squared. 0 squared is 0. 2 times 10 is 20, and 20 times 5 is 100. So this turns out to be 100 meters squared per second squared. And then I have to take the square root of that, right? Because we're looking for Vf, not Vf squared. So when I take the square root of both sides, I get Vf, which is square root of 10 is square root of 100 is 10 meters per second. And I think we want the positive root, right? 10 meters per second. So we can use that new equation to handle situations like this. We'll slide, or actually move the third one. Yeah. So in the second power tool that we're going to derive, imagine a situation like this. We have a car, and it's traveling at 5 meters per second. It begins accelerating at 2 meters per second squared, and it does so for 3 seconds. So it's already traveling at 5 meters per second, then it accelerates for 3 seconds. How far did the car travel during that time interval? Well, guess method again. Our givens and unknowns are here, so we know the original velocity is 5. The acceleration we're given is 2.0 meters per second squared, and the time is 3 seconds, and we're looking for how far. So it could either be displacement or distance, but how far. Again, even with the new equation that we just derived, we don't have an equation that has VO, A, T, and delta X in it. We have pieces of equations, and maybe if we solve them separately, we could eventually get to an answer, and you probably could. I'm sure you could. But it would be nice to have a tool, an equation that has delta x, t, a, and v naught. So that's derived on this last one. And remember, we're going to refer back to those 1, 2, and 3 equations. We'll take equations 2 and 3, this is the middle one and the last one, and let's rearrange them for final velocity. So equation 2 is average velocity is original plus final over 2. And if I multiply both sides by 2, I'll cancel 2 on the right, and I get twice the average velocity is VO plus VF. And then if I subtract VO from both sides, I get 2V average minus VO equals VF. And so I've solved that one for the final velocity. On the acceleration one, I multiply both sides by t, and then I add VO to both sides, and I can solve that equation for final velocity. If this equation in blue is final velocity and this equation in purple is final velocity, then by golly, blue equals purple. They're both final velocity. So twice the average velocity minus the original equals the acceleration times the time plus the original velocity. Okay, we rearrange those and we kind of set them equal to each other because they are. And then we have to add in that first equation. So we dealt with equations 2 and 3. Now we have to do for equation 1. And equation 1 is about the average velocity again, which is displacement over time. So I can just substitute that into this equation. So replace that average velocity with delta x over t. And that's what I've done here, is rewritten that with that substitution made. And then do some algebra. So what I did first is I added VO to both sides. So when I add a VO to the left side, it'll cancel the VO here, and we'll get twice VO over on the right side. So that's what I did to get to this step. And then to get to the next step, I divided both sides by 2. And when I divide everything by 2, I have to divide each individual term by 2. So if I divide this term by 2, that cancels the 2. Here I get 1 over 2, or a half, and 2 over 2, which is 1. And then in the last step, I multiplied everything by t. So every term by the time. Cancels the time here, I get t squared there, and I get VOT here. So the final result here is this nice one boxed in red. Delta x is V naught t plus 1/2 AT squared. By the way, I'm not going to ask you to derive these on a test. I wouldn't do that to you. I'm doing it because I want you to practice the algebra, and because it's good to know where these things come from. Okay, now that we have that new power tool, that combined equation, we can use it on this question from before. So the equation we have is this. Delta x is V naught t plus 1/2 AT squared. And now we can just substitute. So it's 5. Sorry, this is kind of moving a bit. 5 meters per second times 3 seconds plus 1/2 times an acceleration of 2 times 3 seconds squared. Substituting my values in. And so down here, delta x equals 5 times 3, which is 15, plus 1/2 of 2, that's pretty easy, that's 1. And that's 1 times 3 squared, which is 9. And so in the end, my answer is 24 meters. Thanks.